Hello everyone, this is our last lecture video for summer quarter. So in our last video, we're going to discuss something called partial pressure. So previously we've talked about air and how air is a homogeneous mixture of oxygen and nitrogen and other gases. So each of those gases exerts their own partial pressure. And then if you add all of those partial pressures together, you get the total pressure of air. Now, one thing that I thought was really interesting with gases is if you've ever been to the doctor and they've tested your oxygen levels, you'll have probably seen this device before. So this is called a pulse oximeter, and they place it on your finger and it uses light to figure out how much oxygen is in your blood or your oxygen saturation levels. So if your oxygen levels are really low, they can monitor that and see what's going on. But if your oxygen levels are normal, then that can tell a doctor, that you're pretty healthy. So this does use gases in our blood to help monitor our health. Okay, so back to partial pressure. So the partial pressure of a gas is the pressure that each gas in a mixture would exert if it were by itself in the container. So as an example, let's say we have a gas cylinder of just helium and then a gas cylinder of just argon. And then let's say that the pressure of that helium gas on its own is 2 atmospheres, and then the pressure of argon gas on its own is 4 atmospheres. Now, if we mix those two gases together, those two partial pressures are going to add together to create the total pressure, or give us the total pressure. So 2 plus 4 gives us 6 atmospheres of total pressure. So this is a super simple law. We just add these partial pressures together and it gives us the overall pressure. All right, so Dalton's law of partial pressures indicates that pressure depends on the total number of gas particles, not on the type of the particle. And the total pressure exerted by gases in a mixture is the sum of the partial pressures of those gases. So down below we can see that the total pressure, PT, is equal to the pressure of gas 1 plus the pressure of gas 2, etc. So super simple law. So, for example, at standard temperature and pressure, we know that 1 mole of a pure gas will have a volume of 22.4 liters. So, what's really interesting is, let's say instead of 1 mole of a pure gas, we have a mixture. So down below, we can see that in the first container, we have 1 mole of just nitrogen. Now, what if we have a mixture of oxygen and helium? But let's say that we have 0.4 moles of oxygen and 0.6 moles of helium. That will add up to 1 mole of gas overall, and that's the same amount as our pure gas. So the mixture and the pure gas will both exert the same exact pressure of 1 atmosphere. So that's really cool, whether you have a pure gas or a mixture. If you have 1 mole total, it will exert the same exact pressure. And we can see that in this mixture with 3 gases. So we have 0.5 moles of oxygen, 0.3 moles of helium, and 0.2 moles of argon, and it all adds up to 1 mole. So that means it's going to still exert that same pressure of 1 atmosphere. All right, so now I mentioned air earlier and how air is composed of different gases. So air has about 78.2% nitrogen, or is composed of that. It's also composed of about 21% oxygen and then 0.8% of other gases like carbon dioxide, argon, etc. Now, if we add those percentages together, we get 100%. And it's kind of similar to our partial pressures. So let's look at those in the second column. So the partial pressure of nitrogen in air is 594 millimeters of mercury. The partial pressure of oxygen in air is 160 millimeters of mercury. And then the partial pressure of all of the other gases is 6 millimeters of mercury. And if we add those together, we get 760 millimeters of mercury, which is equal to 1 atmosphere. So what we call atmospheric pressure is actually the sum of the partial pressures of all of the gases in air. All right, so let's use this law that we just learned about. Let's say that a scuba tank contains oxygen with a pressure of 0.45 atmospheres and helium at 855 millimeters of mercury. What is the total pressure in millimeters of mercury in the tank? Okay, so we're given two different pressures. We're given the pressure of oxygen, which is 0.45 atmospheres, and we're also given the pressure of helium, which is 855 millimeters of mercury. So what we need to determine is the total pressure in millimeters of mercury. So I notice right away that our units are not all the same. We have one measurement in atmospheres and one measurement in millimeters of mercury. So we should probably convert one of those. And since we need everything to be in millimeters of mercury, let's convert the pressure of oxygen to millimeters of mercury. So remember, 1 atmosphere is equal to 760 millimeters of mercury. So let's just do a quick conversion. All right, so we want to convert to millimeters of mercury. So that should go in the numerator. And then 1 atmosphere will go in the denominator. And then this is a super easy calculation. We just take 0.45 times 760, and that gives us our pressure in millimeters of mercury because atmospheres will cancel. So we'll end up with 342 millimeters of mercury. So that is our pressure of oxygen. Okay, so now what we're going to do is just add those two pressures together. So PT is equal to the pressure of oxygen plus the pressure of helium. So we'll plug in what we just calculated and what we were given. All right, so now let's just add those together. And my calculator tells me that this will give me a total pressure of 1,197 millimeters of mercury. All right, so let's talk about Sig Figs here. How many Sig Figs were we given for each value? just 3, right? So our final answer should also just have 3 sig figs. Oops, sorry. So I'm going to round up because our dropped digit there is a 7. So the 9 will round up to a 10, which means we're really taking this 1 and rounding it up to a 2. Okay, but that gives me 2 sig figs. So maybe we should express this in scientific notation. So let me make some room down below. Because in scientific notation, it's much easier to express how many sig figs you have. Okay, so remember in scientific notation, our coefficient has to be between 1 and 10 or equal to 1. So our coefficient will be 1.2. And then let's put an invisible decimal point on the end here. We would have to move that once, twice, 3 times. So our power of 10 will be 10 to the 3rd. Oh, and I need a 0 here. I forgot. We need 3 sig figs. Oh my goodness. It's definitely the end of the quarter. My brain has given up. Okay, so our final value here in scientific notation is 1.20 times 10 to the 3rd. And that will give us 3 sig figs. Okay, so let's see if we got it right. Awesome, we got the same exact answer. Okay, let's do another practice problem. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atmospheres. If the oxygen has a partial pressure of 1,280 millimeters of mercury, what is the partial pressure of the helium? And we're given a few options down below. Okay, so I'm actually going to encourage you to try this problem on your own and see if you get the right answer. And there are solution slides after this one, so you can double check your work. But also notice you're given 2 different units again for pressure, so you might have to do a conversion there. Okay, and I'll try to skip through the solution slides as quickly as possible so you don't see the answer. All right, so again, there is a worksheet on Canvas that kind of steps through all of these different types of calculations for Module 7. So definitely practice that before you take the final exam. And there is more information about the final exam on Canvas, so please check that out. If you do have any questions, please email or message me. And you guys have been great. I know it's hard to take a chemistry class online, but you did it, you survived. So definitely enjoy the rest of your summer, and hopefully things will be back to normal soon. And I'll see you in person. Okay, bye.